All right, hello, my name is Josh Whaley, and this is the part 3 explaining the adiabatic reversible expansion problems. And in this part, we're going to be taking our first two equations we derived from here, part 1 and part 2, and we are going to use those and kind of mesh them together, melt them together, and explain the relationship between pressure and altitude and also temperature and altitude. We're going to do this in two separate occasions. Okay, so first of all, like I said before in part 2 video, we have, let's say, two amounts of, let's just say, clouds of, or pockets of air. So at position 1 and position 2. So the first one, I'm going to go over pressure first, pressure and altitude relationship. So at position 1, we have some pressure, initial pressure 1, and we also have, it is at position 1 or altitude 1, so it is at Z1. And at the second position, it is at a different pressure, pressure final or just pressure, and at an altitude final, Z final. Okay, so now we're going to use this to represent the relationship between pressure and altitude. So we're going to take our first two equations. So we had our first equation, which was differential change in pressure over differential change in altitude is equal to a negative pressure times mass times gravitational constant over our gas constant R times temperature. In this case, temperature initial, I think, or we'll just leave it as temperature. Okay, and let's go ahead and bring in our second equation. Our second equation, which we got from part 2, is we have temperature 2, or in this case, temperature final position, and we'll just leave that as T, over top of temperature initial, T1, is equal to pressure 1 over top of pressure final, or P2, raised to the negative gas constant R over our heat of vaporization plus our gas constant R again. And we can actually go ahead and simplify this and get our temperature 2, or T final, by itself. So we'll do that by multiplying our T initial to the other side, and we're going to actually also make it easier on ourselves. So when we're going through this derivation here, we're going to actually substitute out our exponent here and give it another name. We'll just call it epsilon. So let's go ahead and do that now real quick. Let's say that this right here, epsilon, is equal to this. So we will remember that later. We'll just know that's our gas constant over top of heat vaporization plus our gas constant again. Okay, so let's go ahead and say that T is equal to T initial multiplied by P initial over our P final raised to the epsilon power. Okay, so now you notice we can actually take, and we have it in terms of T, we can actually plug this into our first derivation, which we got from part 1 video, and we can start solving for the relationship between pressure and altitude. Okay, so we can go ahead and do that. So let's go ahead and say that D, our differential change in pressure over differential change in altitude, is equal to a negative pressure times mass times gravitational constant over our R, gas constant. And now we can plug in our value here for T. So T1, or T initial, and since we have this value right here on the bottom, or the denominator, we can actually do the inverse of it and flip it around. So we can put P initial on the bottom, and bring our P final to the top here. And we can actually also go ahead and say that this is to the first power, and this is to the epsilon power. Okay, so now we have it in terms of this. We can go ahead and start combining our two pressure finals here. And after that, we can go ahead and get our pressures on one side and bring our differential change in altitude and bring it to the other side here as well. And then we can start doing our derivative or integration. So let's go ahead and do that. So we can combine our P values or pressure values here and say that our differential change of pressure over our differential change in altitude is equal to, combine these two, so we can say that negative pressure to the 1 plus epsilon power times our mass times gravitational constant, our R over top of our R gas constant, times temperature 1 or temperature initial, times our pressure initial to the epsilon power. Okay, like I said before, we can divide by our, bring this our P over here, our pressure, and multiply by our dz, our differential change in altitude, and take the integration of that. So we can go ahead and do that now and bring it down here. And let's do that. So an integration of our differential change, let's use blue real quick so you can see it easier. So our differential change in pressure over top of, we brought our P down here, so it's P to the negative 1 minus epsilon power is, and we're going to have these, we're going to have elements of integration here. I'll bring that in a second. So we're going to do, set that equal to, now before, everything in here besides our differential change in altitude, which we just multiplied to the other side, we brought this over here and brought our pressure down below. We're going to use that in the integration. This is a constant, so we can bring it outside of the integral. So we can say that, or on the outside, let me go ahead and fix this real quick, and say that our negative mass times gravitational constant over our R times temperature initial times pressure initial to the epsilon power is on the outside multiplied the integral of our differential change in altitude, dz. And our limits of integration here, since we're doing with pressure and altitude, like I said before when I brought in over here this pocket of air, at initial position, there's some pressure initial, and it's at the initial altitude, which is at z1, a z initial. So we can go ahead and write those in. So we have our z initial and our p initial. And once it goes up to the second position, our p final is at an altitude, our final altitude. So we can go ahead and say this is a z final and p, or just really just say z, doesn't really matter. Okay, so we can go ahead and do the integration of this. So we can bring it down and say that, okay, the integration of this is 1 over epsilon times P initial, this is the initial, yeah, times P initial of negative epsilon, and we'll put that to the, we'll do that to the P to the P initial. I think that's right. And I think that's a negative. So we're going to set that equal to our negative mass times gravitational constant over top of R times temperature initial times pressure initial to the epsilon power. And we can actually go ahead and bring this up and make it easier on ourselves from later. If we have the pressure initial to the epsilon power on the bottom, we can bring it to the top and say pressure initial to the negative epsilon power. Okay. And we can actually bring this up to the front to make it easier on ourselves as well. So let's go ahead and do that. We'll take that. I don't think that's what it's supposed to be. So let's rewrite this as a pressure initial to the negative epsilon power minus mass times gravitational constant over R times T initial. And this is, since we had before, we had integrated to the integration dz, we're just going to say that it is multiplied against z final, in this case z, minus z initial, or z1. Okay, so we're going to go ahead and multiply by negative ez to cancel this out. I think maybe there is there. Yeah, I think there's a negative there. Sorry, I was picking up my signs. So multiply by ez and on both sides, and we are going to then get our pressure and bring it down here. So let's go ahead and do that. So we have pressure, pressure to the negative epsilon power minus pressure initial to the negative epsilon power equals pressure 1, or pressure initial, to the negative epsilon power. And like I said before, we multiplied by a negative epsilon on this side. So we multiply by negative epsilon, which is going to mean that we have a negative and a negative. So these cancel out. So I can go ahead and take it out real quick and write this as epsilon times mass over times gravitational constant over our R times our temperature initial multiplied by our Z, or initial, or final altitude, minus our altitude initial. Okay. And let's see. So if we go ahead and bring our pressure initial, we want to get pressure final by itself. So if we add our pressure initial to the other side and factor it out, we can get pressure final by itself. So let's go ahead and do that. And let's simplify this as P to the negative epsilon is equal to, we're going to add it over and factor it out. So it's going to be P to the negative epsilon times the 1, where we factored out the negative epsilon that we added in, plus our epsilon times mass times gravitational constant over our R, or gas constant, times temperature initial minus, or multiplied against our Z final, or altitude final, minus our altitude initial. All right, we're almost getting to the end here. So now we want to get pressure by itself, or pressure final by itself. So to do that, we can multiply by its reciprocal. So we can multiply by reciprocal on all of these and actually cancel out a few epsilons. So we can go ahead and do that. So we multiply by negative 1 over epsilon, this cancels out. Multiplying this by negative 1 over epsilon cancels it out as well. And this will bring this to the negative epsilon power. So we're going to be left with pressure final, in this case, is equal to pressure initial. I forgot to write that there. Pressure initial to the multiplied by 1 plus our epsilon times mass times gravitational constant, R times T initial, multiplied by Z final minus Z initial. And then since you multiply by negative 1 over epsilon, bring it up here. All right, so our last step here in this relationship, we can actually go ahead and bring in, or actually bring back in what epsilon was equal to. In this case, it was that original exponent, which was negative gas constant over our heat of vaporization plus our gas constant again. So we can go ahead and bring this back in. So let's go ahead and do that. So our final equation is equal to pressure final is equal to pressure initial multiplied. So since there's a, when we're bringing these back in, or plugging it back in, there's a negative value right here. So when we plug in our negative, this turns into a negative. We put this, plug in our epsilon back. So this goes to 1 minus, so we bring in, so it's going to be R times our mass times gravitational constant over R times our CV plus R times temperature 1. And then that's multiplied by Z final minus Z initial. So we can also cancel out an R here since it's R over R and rewrite that and leave it as this. And this is all raised to the negative 1 over epsilon. So going ahead and plugging in our epsilon again, we notice there's 2 negatives, so those cancel out, so it goes to a positive. And it's 1 over epsilon, so we can rewrite this as, okay, that's 1 over 1 over R over our heat of vaporization plus R. And we can go ahead and do this and rewrite our final answer as, okay, this brings CV plus R to the top over top of R. So we can write this as CV plus R over R. And this right here is actually our final answer for the relationship between pressure and altitude. Okay, so as I said before, we need to actually show the relationship between temperature and altitude as well. So we're going to actually really be using this equation again, since it's without actually plugging in and making it really sloppy, and plugging in what the actual value for epsilon is. We can go ahead and just use this equation and plug that back into up here to find our relationship between temperature and altitude. So I'm going to go ahead and do that. And we can say that, okay, we can take our initial equation for right here, which was our temperature final, which we're trying to solve for, is equal to our temperature initial multiplied by P initial over top of, now what was our P? In this case, it'd be, we're going to be plugging in this equation. So what is P equal to? It's equal to P1 minus 1, multiplied against 1 minus M times G over top of our CD plus R times T initial, and that's multiplied by Z final minus Z initial, and this right here on the bottom is all actually, well no, this part right here is all actually raised to the, what was it, the CD plus R over R. CD plus R over R power. Okay? Which we, in this case, we said it was equal to, well actually no, it was raised to this power. My mistake, sorry. So this is plus. I wrote the wrong equation. I'm sorry. Hold on a second. Let me go ahead and fix this. So this is the equation we're using. So it's epsilon plus mass times gravitational constant over R times T1, and then it's Z final minus Z initial. And that is to the negative 1/3, 1 over epsilon power. Okay, so we can go ahead and cancel some things out and make it less sloppy. So we can go ahead and say that there's 2 pressure initials over top of each other, so these cancel out. And if we actually go ahead, and this is all raised to the epsilon power, as we see right here. So we can go ahead and cancel some things out. So we already canceled out the pressure initials. And we can rewrite this. If we say that bring this to the top and bring this to a positive 1 over epsilon, we can cancel it out because this is the reciprocal multiplying by the reciprocals. So we really can rewrite this as temperature final is equal to temperature initial multiplied by 1 plus epsilon times mass times gravitational constant over top of our R, or our gas constant, times temperature initial times our Z, or our final altitude, minus our let's see, our initial altitude. And since, like I said before, we bring these to the top, taking an epsilon, multiplying it by the 1 over epsilon power, these cancel out, so there's no power. And we can go ahead and finish this off. Our final equation, we just plug back in what epsilon is here, and it's very similar to our pressure equation. So it's going to be our temperature final. All right, this is a different color so you can see it. Temperature final is equal to temperature initial multiplied by, since we multiply by negative, we make it a negative again, as before, negative mass times gravitational constant over our heat of vaporization plus our gas constant R times our temperature initial multiplied by our final altitude minus our initial altitude. And yeah, I think that is our final equation. Yep. Okay, so this is our relationship between temperature and altitude, and this is our relationship between pressure and altitude right here, as you can see. So one final note before we do anything else, it is important to note that for temperature, you can notice that when writing this in, for temperatures that are at absolute zero or below zero, this would not work. Because if it was a zero, then everything would cancel out and it wouldn't be possible. So it needs to be, this is only true for certain conditions. So is that conditions above zero temperature, and also depending on the altitude. So say we were raising to a certain altitude was initial, and we raised to an altitude that was out in space. Well, out in space, temperatures decrease by a certain by vast amounts, and also there are solar radiation, which is also heat up the pockets of gas, which in that case would go against what we're doing here. We are working for an adiabatic reversible expansion. In adiabatic, there is no heat added to our equation or our process here. That means dq, as you can see right here, our dq is 0. So if we had solar radiation or some sort of heat added into it, dq wouldn't be 0, and this whole process would be not possible. So we are doing this for a adiabatic reversible expansion where dq is 0 and the pressures external and internal of our pockets of gas here are the same. So like I said before, this is our relationship between pressure and altitude, and this is our relationship between temperature and altitude. Thank you so much for watching. This has been the part 3 of the adiabatic reversible expansion problem, and have a great day.